So thank you for still being here. And I know that seems like a lot of move, but it's fine. So now you're going to hear by Dr. Daniel Sank about dispersive readout and superconducting qubits. He works at Google Quantum AI. And yeah, let's just go along. Get started. We're a little late. So say hi to the speaker.
Okay, thank you. It's a pleasure to be here. I would say if you have a question during the talk, please just raise your hand. And we can do it in real time because I don't think I'm going to talk for a full hour. So I welcome questions. Right, so I'm going to attempt to introduce how dispersive readout works in superconducting. So a brief point of introduction, how did I get here? So when I was an undergraduate, my freshman physics professor was Steve Irving. And at the very end of our freshman physics course, he taught us a little bit about quantum mechanics. And one of the things he taught us was that the universe is intrinsically random. And I didn't believe it. I thought this was completely, no way this was true. And so I'm going to show you a table here of like people who taught things and what they said and what I thought about them, and you'll see how I wound up here. So thought quantum mechanics couldn't be right. Then I got to my, I think it was second semester, sophomore year or something like that. I took statistical physics with Doug Stone and learned that the universe can look random, but it's just because there's information you didn't know about and use statistics. It's all fine. And I thought, okay, quantum mechanics is just stat mech. There's no actual randomness. This is all, we're all okay. Then in my quantum course, we learned about Bell's theorem and the fact that you can't have non-local hidden variables. And I was like, oh my God. Now I don't know what to think. The world's falling apart. But then this guy showed up, Michel Devereux, who we just heard a lovely talk from. And he was teaching a course called Noise and Information Dissipation and Amplification. And never mind the long title, one of the things in that course was the idea that quantum mechanics doesn't apply just to atoms like it says in the textbooks. It can apply to whole electrical circuits under the right conditions. And I thought, okay, if that's true, then the textbooks are lying about other things, and I have to find out about this because I'm very confused. So I went to grad school. John Martinez was my PI. I learned a lot from him about fab, electronics, quantum mechanics. And that's when, at least for me, I finally felt kind of satisfied that, wow, this whole theory actually works. If you can make quantum mechanics happen on a chip the way you want it to happen, and it felt very gratifying. And then I wound up in this room because that guy sitting in the back over there, Murat, invited me to speak. And Murat, thank you very much for the invitation. It's a pleasure to be here. And thank you also to the other organizers. All right, so here's an outline of the talk. First, we'll go over dispersive readout basics. Then I'll do a few slides explaining something called input-output theory. You may or may not have seen this. If you haven't seen it before, if you stick around in this field, you'll see it in the future, but it's almost never explained where it comes from. So I'll spend a few slides explaining what that is and why it's relevant for readout. Then we'll talk about all the non-idealities that happen in dispersive readout. So like, what are the things beyond the basic theory that really come into play when you try to build a readout circuit? And then at the end, I'll give a few comments about the challenges in scaling the way that we do readout up to many qubits, beyond chips with just 3 or 4 qubits. So let's get started. Dispersive readout basics. So probably by now you've at least heard of the transmon qubit. Michel talked about this indirectly in this previous talk. You have a Josephson junction in parallel with the capacitor, and that makes a nonlinear oscillator. That nonlinear oscillator has a potential energy U that depends on the flux in this junction. And it makes a cosine. And here I'm only showing one of the potential minima of the cosine. And within that well reside different quantum levels. So there's the ground state 0, the excited state 1, the second excited state 2, and so forth. The transmon qubit is a qubit when we operate it in such a way that it goes between the ground state and the first excited state. That's how we want the qubit to work. If you happen to have heard my advanced track talk this morning, I talked all about what happens when you go out of that two-state subspace, but we're not going to talk about that much today. Actually, we will. Okay, so what's so hard about readout? The problem is that if you're in this ground state or this red excited state here, there's nothing to measure. These wave functions are the probability that the transmon has a certain magnetic flux. And you can see that for both of these wave functions, the mean of the flux for the 0 state and the 1 state, it's 0. And the same is true if you do a Fourier transform and express these wave functions in the charge basis. again, those expectations values are 0. So there's no simple electromagnetic measurement you can do to tell which state the qubit is in, which is kind of annoying because when you're doing a computation, you need to occasionally read out like, okay, what is the state of my computer? Another confounding factor here is that if this were a classical resonator, you'd be able to think about its sort of trajectory in phase space as going around in circles. So like if I put some charge on the capacitor and then let it go, the charge would reduce and the flux would increase. The energy goes from the capacitor into the inductor, and then it goes back into the capacitor with the opposite sign. The energy oscillates back and forth between these two. And in this charge and flux plane, you go around and around in circles. The problem is in quantum states, if you're in the ground state or the excited state, these states have definite energy, but they have completely indefinite phase. So the ground state in this phase plane would just look like a ball at the origin. The first excited state, to some approximation, I'm kind of glossing over the details, kind of looks like a donut. And there's no phase you can measure. So there's no charge, there's no flux, there's no phase. It's like, how on earth are you possibly going to measure this qubit? The funny thing is, the fact that it's hard to measure is partially why it's a good qubit. You don't want the qubit interacting with the rest of the environment in ways that you're not controlling. It's kind of nice that the transmon is kind of hard to talk to, but it makes readout difficult. So what are our options? Well, like I said, these are energy eigenstates. So the obvious things you could say, well, why don't I just do an energy measurement of some kind? That would help me distinguish between the ground and excited state. The problem is that at the frequencies that these things usually operate, the energy difference between these two states corresponds to about 0.2 microelectron volts, and that's really small. You can't use like a photodetector to detect that. You need something else. So that's kind of a non-starter. But I mentioned before that, or at least Michelle did, that this is a nonlinear oscillator. And so a very interesting property is that when you go from the ground state to the excited state, the impedance changes. Another way to think about it is that the resonance frequency changes a little bit when you go from one state to another. And that's what we're going to leverage. So here is an oversimplified picture of how dispersive readout works. You have the transmon. You have the transmon, and it's either in the ground state or the excited state, shown here by either blue or red. Those two states have different impedances. So if I hook this thing up through a capacitor to a transmission line, and I shoot in a microwave pulse with amplitude V in, that will reflect and come back down the transmission line with a different amplitude V out. And because the impedance of this thing on the end is different, the phase of these two reflected pulses will be different. This is the basic principle of dispersive readout. Notice that I'm overcoming the energy problem by supplying the energy externally. So the fact that the qubit state energies have a very small difference doesn't matter. I can give as much energy as I want to this measurement to kind of increase the signal to noise ratio up to non-idealities that I'll talk about. Okay, so that's basically it. In practice, the total energy in this readout pulse tends to be like 60 times the qubit energy. So you can see, yeah, we're getting a nice advantage here by supplying our pulse. Right, so let's get into some of the details. Let's talk about the phase and magnitude of reflection in a microwave circuit. So we have this V in and we have this V out. If the transmission line were terminated in an open circuit, the whole pulse reflects with a sign of 1. So like the pulse comes back exactly how you sent it. So if I were to scan, stop working. Oh, it's just very, very good. Done. All right, well, I'm going to plug my hands. If you were to scan the frequency here, both the phase and the magnitude of the reflected pulse would be constant. The magnitude is constant because all the energy is coming back, and the phase is a constant because it's an open circuit. Okay. Now, what happens if I stick a resonator here instead? Now what happens is that the magnitude is still constant because all the energy has to reflect. There's no resistors anywhere. But the phase winds around the circle once. So when you're far off resonance, let's say you have a phase of 2 pi, and as you go through the resonance, the phase goes down to 0. Were you raising your hand?
Yeah, so the question is the state initiated by V in for 0 and 1?
Is the state initiated?
Yeah, by V
no,
in,
so
by the input voltage.
The state of the transmon is set by controls that you do to the transmon itself. I'm only talking about how you read that state out. So the transmon is in either the blue or the red state. You shoot in the pulse shown in black, and then it comes back with one phase or the other, corresponding to whether the qubit was in one state or the other. Right, so as I was saying, if there's a resonator on the end of your transmission line, then as you sweep the frequency of the pulse, you'll see that the phase winds once around the circle from 2 pi down to 0. The width over which it makes that winding is called the line width of the resonance, which we denote by the symbol kappa. And you're going to see that a lot in the rest of the stuff. Okay, so typically when working with these kinds of systems, whether you're a communications engineer doing microwave stuff for cell phones, or you're doing readout for superconducting qubits, it's very common to plot the amplitude and phase in a plane rather than showing 2 separate plots. So I'm going to introduce this picture in the bottom left. So here we have the real and imaginary part of S11. I should have mentioned, what is S11? S11 is the factor that you multiply by V in to get V out. So like if the phase comes back 180 degrees rotated, S11 would be -1. If it's a 90-degree rotation, S11 would be I, because you use imaginary numbers just to make the arithmetic easier. So we tend to plot these things in a plane. And you can think of the axes as either the real and imaginary parts of the reflection, or sometimes they're called I and Q. There are actually several different terminology sets. And I might accidentally use both, so pardon me ahead of time. Anyway, if I'm far below resonance, okay, so that's the left side of the graphs in the top right, then I'm at a 2 pi rotation, let's say, which is here. Then as I approach the resonance, the phase is wrapping around, but the amplitude staying the same. So I trace out a circle in the IQ. The resonance is the point on the real axis over here. And these 2 red dots where I'm on the imaginary axis are kappa frequency apart. So if kappa is 1 megahertz, the frequency difference to go from here around to the bottom would be 1 megahertz. So now let's say that instead of a resonator, we have a qubit, which is kind of like I said, it's a resonator that could have 1 frequency or a different one, depending on its state. So now what's going to happen is I'm going to get these phase curves, but they'll be offset in frequency. Let's think about this. So if the transmon in its 0 state is at a higher frequency, then that means that this curve is just shifted over to the right. The point where you go around that resonance is at a little bit of a higher frequency. And the 1 state puts the qubit at a little bit of a lower frequency. So the curve happens a little earlier as you go around. So the way you do readout is you put your pulse frequency right in the middle here. So if the qubit's in the 0 state, you get 1 phase. And if the qubit's in the 1 state, you get the other phase. And those phases are separated because the curves are offset. So in my circle picture, if the qubit were in the 0 state, the reflection is, say, +I. And if it's in the 1 state, the reflection is -I. There's experimental data there on the right showing that this indeed works. So the qubit was prepared in the 0 state, and then in the 1 state, you shoot in a microwave pulse, you get it back, you analyze it for its phase and your magnitude and phase, and you plot it, and you get what's shown there. Now you'll notice that I don't just get 1 point for the 0 state and 1 point for the 1 state. I get a cluster, and there's these big diffuse clouds. And that's because of noise. There's noise in the system. And so what happens when you gather all the signal and there's noise on it is it takes what would be an ideal point at either, let's say, 0 or 1 here, and scrambles it a little bit in a neighborhood. So part of the game of dispersive readout is having enough signal that those clouds are separated by more than their widths. If those clouds are too overlapping, then you wouldn't be able to tell which state. Okay, this is the base that's really kind of the basics of dispersive readout. So I'm gonna pause for a minute. If anybody has any clarifying questions, it'd be a good time. Yes, please.
So you have this microwave, you send it, it hits the qubit.
Yeah.
What is it reflecting off of? Like, what's the reflection?
What's the reflection?
Right, because like you're saying that you get a signal from it, you return back.
Yeah.
And there's some kind of phase shift
Yeah.
to the signal.
Yeah.
So what's causing that phase shift?
So it's just like with light. So you know how if you if you fill a glass with water and kind of look at it sideways, the light's kind of bending.
Yeah.
That kind of physics happens in circuits also, whenever you have an impedance change. So in optics, light is traveling through the air and then it hits the surface of the water and it bends.
Right.
In microwave circuits, whenever the impedance changes, you get a partial reflection. So the transmission line has some impedance, and the wave is traveling along just like optical light traveling through air. And then this capacitor and this resonator have a different impedance. And just like an index of refraction change, some of the wave bounces back.
And you're saying the ground and sides, they have different impedance?
Yeah, because it's a nonlinear circuit. Yeah, that's kind of like one way to think about it. This might help. This potential kind of rolls over at the top because it's a cosine.
Yeah.
So the higher you go here, the lower the frequency gets. It's just like in a classical system. Like if you have an oscillator whose potential like rolls over, the more energy you put in it, the lower its frequency. So the transmons the same thing. So you can think of it as an
Oh,
impedance
I guess,
change.
yeah, it's like traffic.
Yeah.
Yes, that's frequency.
Yeah, exactly.
So why doesn't it interact with the resonator? Like, why doesn't it change the state of the qubit?
Why doesn't the readout change the state of the qubit?
Yeah, like you are sending
Yeah.
a signal.
Okay, so there's two answers to that. The first is that I'm kind of lying to you. This is not the full circuit. I'm going to introduce some more details in a minute. But the other answer is that it does. The readout does affect the qubit. We don't like that, but it does happen, and I'm going to talk about that.
Is that does that also show up in the figure you were showing? Like
So here,
yeah, so the zeros and ones aren't exactly where they're supposed to be.
yeah,
Like,
it's very interesting. If the readout pulse is weak enough, it doesn't really affect the qubit state. But if you drive too hard, it completely messes up the qubit, and I'm going to talk about that in detail later. Yes.
Yeah, got a couple of questions online. First one is, why is the magnitude constant while probing the resonator? That is, does an impedance mismatch cause some energy to get transmitted?
No, because if you look at this, there's no resistance anywhere here. So that wave has to reflect. It's true that there's an impedance mismatch here. There's a ground here, and there's a ground here. So at the end of the day, all of that pulse energy will return.
Another question that is, does the resonance of the qubit correspond to the 0-point fluctuations introduced earlier today or earlier?
When people say 0-point fluctuations, what they're usually talking about is the width of these wave functions. That's not the same thing as the frequency of the qubit, which is the energy difference between the 0 and 1 state. Those actually are related, because if you change if you literally go like change the capacitance of the qubit, it will change the 0-point fluctuations and the frequency, but they are independent concepts. Independent concepts that depend on the same things.
Quick question also, dispersive shift is measured at phase equals to pi.
Might not have. Yes, I forgot to say. Right, so I forgot to introduce the term dispersive shift. So the dispersive shift is the frequency offset between these two curves for the qubit 0 and 1 states. The question was, is it defined in pi? Well, it doesn't really matter. The dispersive shift is the frequency translation between these two curves. And I should also say that, in this picture, I drew the blue on top and the red on bottom. And here you see the blue on the left and the red on the right. That's just because the absolute phase of that reflected signal depends on how long your transmission line is. So this whole piece of data can be rotated around arbitrarily without any.
And then a final question that are sort of related. State 1 and state 2 at different frequencies, and sort of the question is what defines the state. And the other one, which is related, is what does it mean to be in resonance? Does the input voltage, is that one on resonance with the frequency omega 0, 1, so between the two states?
Yeah.
Yeah.
Okay, so the first question was, what defines the state? Okay. So yeah. Typically, when we talk about the states of a transmon, we're thinking about this picture here in the top left. So you have a system. You can write down the Hamiltonian just like you would for the Hamiltonian of a particle box or a harmonic oscillator or whatever. And you can solve for the eigenenergies and the waveform, the eigenstates and all that stuff. And you can express those as functions of, let's say, flux. So where you might think in space of having like an electron wave function that's a function of position, here we're writing the wave functions as a function of the flux in the Josephson. And they look like that. So the states that I'm talking about are literally these states. Just like the wave function of a particle in space, you can write the wave function as a function of position or a function of momentum or other things if you want. It's common in our field to draw the wave functions as functions of flux. In some types of qubits, it's more convenient to express them in terms of charge, kind of depends on the device. But for transmons, usually you'll see them drawn in terms of flux, and those are the states. What was the second question?
What does it mean to be on resonance? Is the input voltage on resonance with the frequency of the 0-1 transition,
Yes.
omega 0-1 for both cases of 0 and 1?
Yes, that's exactly what I mean by that.
Yeah. Perfect.
So in the data line, one state or the other drop the phase to pi earlier or later. Okay, right.
Yeah.
Yep. Definitely.
So let's take the simpler case, no qubit, just an LT resonance. In this case, you can go plug this into SPICE or whatever you want. If you look at the phase of the reflected signal as a function of frequency, it will do this. It will go from, it'll make a difference of 2 pi as you go past the resonance frequency of the resonance.
At high frequency, shouldn't the capacitor be shorted? So you short it and
Yeah.
and then shouldn't it be reflected with pi?
Shouldn't it be reflected with pi phase? Yeah, hold on. That's a really good question. We can think about that for a second. Okay, I think the argument you're making is that if you're way below resonance, this looks like an open.
Yeah.
Because of the first capacitor.
Right.
And if you're way above resonance, it should look like a short. So it sounds like I'm lying to you, and it shouldn't go around 2 pi. That's a good question. I didn't think very carefully about this. I don't remember. I'm not going to be able to figure it out standing up in front of you because I'm not thinking about it. It's a very good question, and we should run this down after the talk because now I'm curious to. Yeah, it's a good point.
Right. And then the second one is how the state changes.
Well, basically, what happens when you have the nonlinearity is that the resonance frequency of this thing is different depending on which state it's in. So if the qubit is blue, ground state, it has a certain frequency. So you get this curve. If the qubit's in the excited state, its resonance frequency shifts a little. So you get the same curve, but it happens at a different frequency. The crossover is at a different. That's it. Does it make sense?
Makes it overall.
Oh, the physics of why the frequency.
Why like if the resonance frequency changes, then it shifts its left or right.
Well, so as soon as I drew this picture, I had to put the center point somewhere. That's the resonance frequency of this. So wherever that resonance frequency is, that's where the curve is going to cross.
And it will be reflected to its phase equal to 90 degrees or something.
Well, now I'm nervous about answering that because you stumped me with the other question. So I'm not going to answer that yet, but we should figure this out later because.
What distinguishes sending in a signal to read out versus sending in a signal to excite even at the 0 state to the 1 state?
Excellent segue to my next set of slides. Okay, so there is a major problem with what I just told you. I told you I was gloss. I gave you a simplified picture. It's a simplified picture for the following reason. So I said that kappa was the line width of the resonance. Kappa is also the time it takes for energy. If I put some energy in this resonator, kappa is the time it takes for that energy to leak out. So if I were to excite this resonator and look at the voltage as a function of time, it's oscillating, but the magnitude of oscillation exponentially goes to 0 because energy is leaking out through this capacitor into the drive circuit. Okay. So that presents a big problem for readout. You can't actually use the circuit that I drew. If you did this circuit, then the time it takes for energy to like get in and have its phase shift and then come back out, which is kappa, that would also be the time it takes for the qubit to just die, which is terrible. Like because that means that if I excite the qubit and try to measure it, it has a pretty high probability of decaying before the measurement is finished. In other words, by attaching a transmission line to the qubit like this, I'm giving the qubit a place to dump its energy. And if the time scale for dumping energy is the same as the time scale for readout, you can't do a very good readout. So what we actually do, and now I'm not lying anymore, this is what readout circuits really look like, is you have a resonator connected to the qubit between the input-output line and the qubit, just like this. So what's the idea here? The idea here is the following. The resonator frequency, omega r, is very different from the qubit frequency. It's separated by like a gigahertz or more. So at the qubit frequency, so in the line of this gentleman here was asking about being off resonance of resonator. If the qubit is way below the resonance of the resonator, then the qubit mostly sees this inductor as a short to ground. So energy can't leave the qubit at the qubit's own resonance frequency because it just sees ground. It doesn't see the path out the readout line. So the qubit T1 is still maintained. But the changing impedance of the qubit when you go from one state to another still slightly changes the resonance frequency of the resonator. So you can still do a readout. So you still get these separated blue and red curves at the resonator frequency. So now my readout pulse that goes in here is at the resonator frequency, not the qubit frequency. And I have this these separated curves where I can see a phase difference. But down here at the qubit frequency, its decay lifetime can still be high. If you put the qubit closer and closer to the resonator, its lifetime goes down because on resonance, this resonator looks like an open. A parallel LC resonator looks like an open resonance. So if it's open, it's like it's not there, and now all the energy from the qubit can just. So the T1, this black line, the T1 goes down at the resonator. So this is how dispersive readout actually works. You connect the qubit to a resonator, you detune them, and your probe signal is at the frequency of this thing, not the frequency of the qubit. So for the gentleman in the back who just asked, how is it that the readout signal isn't just driving the qubit? The answer is that they're two very different frequencies. This is another good opportunity to take a couple of questions. Go ahead.
So I was also gonna ask earlier, but maybe that just answered. So S11 in this case.
Yeah.
Or these two cases depends a lot on frequency.
Yeah. Okay. Yeah, S11 being frequency dependent is that's like the whole crux of how it works.
So two online, going back to the noise plots that classify the
Yeah.
0, 1, are those noise, or are these plots related to the probability of being the 0 or 1 state?
Yeah, so yes. So in this particular case, the points that I colored blue are cases where I intentionally initiated the qubit in the 0 state and then looked at the reflected signal. The points that are colored red are the cases where I initialized the qubit in the first excited state and looked at the reflected signal. So you'll notice that the blue and the red are mostly separate. Now, if you look closely, there are some red points over here. And those are cases where I excited the qubit, but then before the readout could finish, it decayed into the ground state. So I colored the point red because those are cases where I prepared the 1 state. But the point winds up with the blue because the qubit was actually in the ground state when the readout happened.
Coming back also, from the red-blue curve showing the dispersive shift, seems like the resonant frequency, omega 0, 1, is changed depending on whether the qubit is in 0 or 1 state. So the spacing between the 0 and 1 changes depending on what the qubit state is.
I didn't follow that.
Yeah. From the red-blue curves showing the dispersive shift, which is the upper one. Seems like the resonant frequency omega 0, 1 is changed depending on whether the qubit is in the 0 or 1 state.
Yeah.
So question is, does the spacing between 0 and 1 change depending on what the qubit state is?
Well, the spacing between 0 and 1 is the difference. If this blue curve and the red curve are the curves you get at the qubits in the ground state or the excited state. You get one curve for each case. And the difference is what we call the dispersive shift, denoted by 2 chi. And by the way, I should mention numbers. That's usually around like 1 to 5 megahertz, just to give you an idea.
Actually, a question from me.
Yeah.
Regarding the classification, how are there methods of using certain classification kind of methods, algorithms to improve the readout fidelity?
Yeah, there's a lot. There are
Like
papers
machine
about-
learning and stuff like that, that probably could.
There are papers about that.
Yeah.
It's an interesting thing. There are papers about more sophisticated. So, okay, the obvious thing is you draw a line.
Yeah.
And you say, if I'm on the right, it was a 1 state. If I'm on the left, it was the 0 state. There are papers about more sophisticated classifiers.
Mhm.
Typically, they only help you when the readout error is kind of large,
Mhm.
which you don't want to be in that situation anyway. In situations where the errors are relatively rare, those methods don't tend to help much. I think that probably. The other thing to keep in mind is when you're running a quantum computer and you're doing error correction, you have to keep measuring the qubits. You have to do a cycle that only lasts about a microsecond.
Mm.
So you don't have time to send the data to a computer, run a machine learning, run a neural network, and then get the information back. Typically, you want to do something that you can compute pretty quickly on an FPGA.
Mhm.
So there's a latency issue that comes into play also. Yes, please.
I think that's it.
Yes.
Yeah.
So as I mentioned before, the phase of the reflected signal depends on the length of the transmission line. So if you don't calibrate that out, you'll have an arbitrary rotation that just doesn't mean anything.
Okay.
So although I've been drawing things this way, this 90-degree rotation is there because there's just some length of cable. Things are rotated. So to deal with, just to recap, to deal with this problem where you can't just directly hook up your readout line to the qubit, you interrupt it with a resonator and you put them at very different frequencies. You use the resonator's frequency for readout, and that preserves the qubit lifetime. Because at the qubit frequency, this resonator looks like a shell. So that's how dispersive readout actually works. We can skip that. Okay. Now what I'd like to talk about is do a little math, show some theory, because you will inevitably see some of this stuff in papers, in books, and talking to other people, and it's very hard to track down where some of the modeling techniques for readout come from. So I'm going to introduce them in painstaking detail. I'll share the slides later. Everybody will have them. So even if you don't follow all the equations now, that's okay. You'll have heard the words. You'll be able to follow it. So let's answer first one question. How do you compute this dispersive shift? So the qubit can be in one state or the other, and claiming that there's going to be a phase, a frequency shift in this resonator by some amount. How would you compute that? Okay, so the way you do it is you draw the qubit capacitively coupled to the resonator, and then you go through the procedure that Michel started talking about in his talk. We write down a Hamiltonian. So how does that work? There are some variables that make the calculation a little simpler. So instead of just the capacitance of the resonator, there's a sort of renormalized capacitance of the resonator, which is essentially just the resonator capacitance plus the coupling capacitance. Same thing for the qubit. And then that coupling capacitance CG also gets renormalized to this funny looking thing. Don't worry about where those came from for now, but they're there for reference because you might want to look at that later. And then if you follow the prescription that's in Michelle's old lecture notes, or now there's even books, you can write the Hamiltonian for this system. So you have the energy in the qubit's capacitor, the energy in the Josephson junction. That's the cosine term. Oh, wait. Somebody's, yeah. You have the energy in the resonator's capacitor, then the energy in the resonator's inductor, and then the coupling term. So the coupling term has the product of the qubit charge and the resonator charge divided by capacitance. Okay, so you write that down. Great. What do you do with that? So what is done in the literature is a series of approximations that look pretty innocent. Actually, it turns out that these approximations can be pretty bad in some cases, and I'll comment on that later. But what people usually do is they just pretend the qubit only has 2 energy. And so what you wind up doing is you convert, you look at the matrix elements of the charge and flux operators, and you just truncate them to the bottom 2 levels. And when you do that, you can re-express the Hamiltonian like this. So this is the energy of the resonator. It's omega times A dagger A, which is the number of photons in the resonator. You have the qubit, which is the poly Z matrix. So that's one of the poly matrices. It has a 1 in one corner and -1 in the other. So the qubit has 2 states. And then you have the coupling term. You wind up getting a prefactor that we call G. And then you have a bunch of terms here. This term means add a photon to the qubit by subtracting 1 from the resonator. This is the opposite. Take a photon from the qubit and put it in the resonator. And then you have these 2 funny looking terms where you either add a photon to both the qubit and the resonator, or subtract a photon from both the qubit and the resonator. Okay, that's still not that enlightening. So the next thing that the next sort of apparently innocent thing that people do is they say, well, I don't like these terms, these 2 last terms, because they don't conserve energy and they don't conserve the number of photons. So let's get rid of it. That's called the rotating wave approximation. It's actually a pretty good approximation when you're calculating eigenvalues, but it is terrible when you're trying to understand dynamics. And I'll explain why later. But okay, we throw those away. So then we wind up with this. We have resonator energy, the qubit energy, and the coupling, which has a certain prefactor and can move photons from either the qubit to the resonator or from the resonator to the qubit or from the qubit to the resonator. Then there's the hard step, and it takes some insight to understand why you should do this. But you can look this up. There's actually a mathematical technique that's really good to know. It's called the Schrieffer-Wolff transformation. It's basically doing perturbation theory, where your small parameter is G over delta. So G is the coupling strength between the qubit and the resonator, and delta is their frequency difference. If that thing is small, you can do perturbation theory. And if you do that, you wind up with this Hamiltonian on the bottom, which is really pretty looking for the following reason. You just have the resonator energy, the qubit energy, and a coupling term. Well, let's investigate the coupling term. You could look at this and say, okay, this Hamiltonian term is proportional to n, the number of photons in the resonator, just like the resonator's own energy. So you can think about this as if it's a shift in the frequency of the resonator that depends on which state the qubit is in. If sigma z is +1 or -1, you either get a positive or a negative contribution to the resonator's frequency. So like I said before in my previous slides, the resonator frequency shifts one way or another, depending on which state the qubit is in. And that's how readout works. That's the basic principle. You can also find pretty quickly from this, you see how, so sigma z is either going to be +1 or -1. So the frequency difference is twice this prefactor G squared over delta. So the dispersive shift is, well, got a minus sign, so it's minus G squared. And that turns out to be a pretty good formula. If you measure experimentally, what's the dispersive shift? That formula works pretty well. So even though you've made a couple of suspicious approximations, they actually work for computing the dispersive shift. Another way to look at that term is that it's proportional to sigma z, just like the qubit's energy. So you can think of it as a change in the qubit frequency that depends on the number of photons in the resonator. And that's called the AC start shift, which is a term you'll hear all the time. Great, so we've computed the dispersive shift, and it's pretty good. But this is a bunch of true lies in the sense that I just said. It's good for computing the dispersive shift. It's very bad for other things, and I'll explain that. Okay, so now that we've done that, now let's talk about input-output theory, which is how you describe the dynamics of the readout process itself. The first question.
Please go back to the previous slide. So you can also view this as change in qubits frequency, right?
Yeah.
Which is not good.
No, it's mildly annoying. It means that when while you're doing readout, and this n goes from 0 to some number, the qubit frequency will shift down.
Okay, but won't that change the state of qubit, like between 0 and 1?
No, so you're changing the resonance frequency of the qubit, but not its state. So to kind of get your mind working, suppose I have a particle in a box and I'm in the whatever first excited state, and I slowly push the walls together. The transition frequencies between the states will increase. But if I do this slowly, you'll stay in the first excited state. Yeah. That makes sense.
But you have a different resonance frequency now.
Yeah, the qubit frequency is changing, that's right. Typically during readout, the qubit, this, like I said, this would be a few megahertz, and n might be like somewhere between 5 and 10. So the qubit frequency will shift by a few tens of megahertz during readout, which is not really a big deal. It's a small change. I mean, the qubit's at 5 gigahertz, changes by 20 megahertz. It's not small. So we talked about the basic theory of how to get the dispersive shift. Now let's talk about how you actually model readout, like the time dynamics of readout itself. Because this is hard to dig up in the literature. Okay. First, I want to define a few concepts. So we send in a signal, it bounces off, it comes back, we collect it, we make these plots. How well did we do? Like, can we say something about the error in our readout given other properties of the system? So if I take these two clusters of points and collapse them onto a line that connects their centers to make a one-dimensional plot, you get something like this histogram shown here. So you have the points from the one state, the points from the 0 state, points from the 1 state. They're separated by some amount that I call x0 minus x1, and they have some width signal. There are different definitions of the signal-to-noise ratio. The one I like is here. SNR is the separation squared over twice sigma squared. And in that definition, the separation error, which means the probability that a blue point is on the right or that a red point is on the left, so it's just the overlap of these distributions, it's given by that equation in the top right. So there's the complementary error function and the square root of the SNR. Okay, so that's fine. If you can calculate how far apart these clouds are and how wide they are, you would be able to predict the error in the readout. But how do you predict this signal-to-noise ratio? Turns out you have to do an integral, and it looks like this. It looks kind of funky, so I'm going to talk you through it. So what you do is you look at this outgoing wave, which I believe is B. B is different depending on whether the qubit is in the ground state or the one state. You just take the difference. And if you want, you can add a weight function here. And the reason you have a weight function is like, if you know when the readout starts and ends, you only want to do the integral when there's a signal. So like, this is really just a function that's kind of like choosing where to do the integral. It's like a selector function. So you take the difference, multiply by the selector function, and integrate, you square that. And then that gives you the separation. That's the x0 minus x1 squared part. And then you just integrate the selector function squared, and that gives you the noise contribution. And the ratio is the SNR. Up to a little prefactor called 2 eta. And what is this? Eta is the fraction of energy that you collect. Between your qubit and your room temperature instrumentation, some of the energy is going to get lost. Cables are not perfectly conductive. Amplifiers are imperfect. And so this thing just characterizes how much of the signal you collected. So eta can be between 0 and 1. So that integral is how you compute the SNR. There was a question?
When you have two coupled oscillators, can they end up being chaotic just like in coupled pendulums? Does this need to be considered during readout and circuit design?
Yes, that's a very good question. If you've heard of readout-induced state transitions or measurement-induced state transitions or ionization from readout, that is, in a sense, a chaotic process that happens when you drive the readout too hard. And if I have time, I will talk about that, although I'm not sure I'm going to get to it. But yes, you can absolutely get chaotic behavior. It's very bad. All right. So if you know the outgoing wave amplitude, you can just stuff it into this integral to get the SNR. But how do you compute that out? I'm now going to show a series of 3 or 4 slides that are really a lot of equations. And again, the point is for you to get some glimpse of how this whole thing works. Not that you're going to memorize it right now today. Feel free to talk to me after the lecture. You can email me, ask your friends, ask your professors. I just really want to make sure people kind of have some idea of how this works, because papers just throw out the results and don't really tell you where it's coming from. Let's consider the following system. We have an LC oscillator. It's driven by a charge, like a voltage drive through some capacitor. And let's say it's also driven by a current through some mutual inductance. How do you, as a physicist, as an engineer, calculate the dynamics of this? What are the equations of motion? Kirchhoff's laws. And you can just write them down. So here I'm using for my my variable of flux in this inductor. That's phi. And if you just remember Kirchhoff's laws and write everything down, you get this equation of motion. Second derivative of phi, you have phi itself, you have, and then on the right-hand side, you have the drive terms. So you have the derivative of the drive voltage, and you have the drive current with a bunch of prefactors, and you can work those all out yourself. It's worth doing it once in your life. And then there's a procedure that you probably learned in a mechanics course where if you have a differential equation, you can basically by guessing figure out what the Lagrangian is, and you can convert that to a Hamiltonian. There's not really a recipe for finding the Lagrangian for a system. You really do kind of have to guess and check. And once you've done it a few times, you get pretty good at guessing. So you wind up with a Hamiltonian. It has a phi squared term, a charge squared term. It has some drive terms. This still isn't that enlightening, but that's the first step. If you were to turn the drives off and just look at what happens dynamically to this system with no drives, you would find that in the phi q plane, it goes around in circles. This is what any oscillator does. It goes from having a lot of potential energy to having a lot of kinetic energy and vice versa. So the first thing that you do to clean this up is you stop working with phi and q, and you work with dimensionless variables, which I call x and y. And the way you do that is like this. It turns out that if you find the 0-point fluctuations of the charge and flux, those are given by these equations at the top. The useful variables are where you just divide phi and q by the 0-point fluctuations. Those are dimensionless, and they really clean things up because instead of getting an ellipse in the phase plane, you get a circle, which enables the next step that I'm going to explain in just a second. That Z up there is the impedance of the resonator. That's just the square root of L over C. Okay, so you go to these dimensionless variables and you just do a bunch of substitutions. There's nothing fancy happening here. And now the Hamiltonian looks like that. So now you have x squared plus y squared. You still have the drive terms, but it's a little more symmetric, which is nice. That enables the next step, which is something that many of you are probably familiar with, where you go to raising and lowering operators. And those are defined like this. It's a plus a star over 2 and a minus a star over 2i. By the way, none of this is quantum. This is all classical physics. Like, it all works classically. You do that, now the Hamiltonian is super simple. It's h bar omega a star a plus z of t, which is just some renormalized drive thing. It's just the current and flux drive with a bunch of prefactors. Don't think too hard about it. And the nice thing about doing this is that the equation of motion for A is a first order differential equation. It's simple. A dot has a drift term. That's the resonance frequency of the resonator minus I omega A and plus the drive. So that's way simpler than that second order differential equation we got from Kirchhoff's laws. And frankly, this simplicity is why Hamiltonian mechanics is kind of useful. You go from a second order equation to a first order equation by going to A variables instead of phi and charge. You get this extremely simple looking equation that you can literally solve by. Okay, but then you make one more simplifying thing. It's convenient to spin the coordinate axes at the resonance frequency of the resonator. That's called the rotating frame. And you do that by just saying, okay, instead of A, I'm going to work with B, which is A times exponential time dependence. So when you do that, the equation for B winds up looking like this. So instead of having omega naught as the drift frequency here, you get omega naught minus big omega. So if you pick your rotating frame frequency to be omega naught, this term disappears, which makes it even simpler. You're just going into a rotating frame where the oscillations are there. So it drops a term. Typically for readout, actually the convenient place to put the rotating frame frequency is in between the frequencies of the resonators for the 0 ones. That's kind of like the center of all the action. So any dynamics are going to be kind of small frequencies around that. And when you do that, you wind up with this. So the resonator has a drift term that's just chi, and that's because you put the rotating frame in the middle of the 0 and 1 state resonance frequencies. So the resonator is either plus chi or minus chi away from that. I've inserted by hand here the decay. I didn't talk about how to do that in Hamiltonian formalism because it's annoying, but you can. So there's the decay, this is just energy loss, and then you have the drive. So what's the point of all of this? The point of all of this is that once you can relate the drive on the resonator to its internal field B, you can put everything together like this. The drive that's applied to the resonator is related to this incoming wave amplitude, A. And the reflected wave amplitude is equal to A times square root of kappa times the internal. Okay, I know this is just way too many equations, but here's the point. The point is, if you know A, because you're driving the resonator, you stick it into this equation, you solve for B. It's a first order differential equation, super easy to solve. Once you know B, you stick it into here, and because you know A and B, you know the reflection. That's it. You're going to see this a lot, this pair of equations. If you read papers on readout, they all talk about this. And I just want you all to know that you can get here from Kirchhoff's law. This is not magic. So a lot of the papers, it's very hard to dig up references explaining where this all is. Right. So once you've calculated the output wave B, let's just go back to here. You stick it into your SNR formula, and you can compute the SNR. And that's basically what I want. We're getting really low on time. I think well, let's see, how many questions do you have?
With 3 online, mostly kind of related to noise. What are some approaches to better filter out noise and dispersion to get the output of either 0 or 1 behavior? Is this similar to how we apply filters in circuits with low pass and high pass? I think the question is, how do you, how's better approaches to kind of distinguish 0 and 1 in the readout? Would you use filters like in a low pass, high pass fashion?
Yes, this is a very good question. And it's not a simple question. Yes, you should have a bandpass filter in your system that only allows signals and noise close to the frequency you care about. So that's close to the frequency of the wave A going in. And beyond that, you want amplifiers that don't add much noise. That's why we use these special Josephson parametric amplifiers. We use hemped amplifiers as the second stage of amplification because they're low noise. Those are basically the
Question about the SNR ratio. Why is the eta outside of the integral? Shouldn't it be different for the 1 or 0 state, as there are 2 different resonators with different frequency? Why should the fraction of energy determine?
That's a great question. You're driving at the same frequency regardless of the qubits. So the frequency of the pulse is always the same. It's only the phase that gets shifted by the reflection off of the readout circuit. So eta is, even if eta changed, we're changing, okay. If you look at your system over like a gigahertz of bandwidth, eta will change a lot. Your amplifier gain depends on frequency. The loss in the cables depends on frequency. But if you're working over a very narrow band, like you are to do readout, where you're just sending in a pulse that's maybe a few hundred nanoseconds long, eta is usually quite constant over that frequency range.
And final question, has the chaotic behavior been studied for readout? Are there any patterns in the chaotic noise, like quantum scars, or maybe something useful that could be used for the likes of like quantum differential piracy or analyzing characteristics of classical chaos?
Okay, this is an excellent question. I don't have time to talk about this now. I'm happy to chat with people about this later if they want. There is a huge history of what is now understood to kind of be chaos during readout. This slide shows a sort of history of papers. This Cohen 2023 paper, the second to bottom, specifically talks about the analogy between classical chaos in a driven pendulum and the chaos caused by readout of the transmon qubit. I would encourage people who are interested to look through this list of papers because this has been a fascinating problem that confounded our field for a really long time. And I love it because I was like involved in resolving it. It was really fun and gratifying to figure it all out. But yes, there is chaos and there's a lot of research in it. Okay, I do want to make a comment about scaling. So this is a diagram of what all of the stuff that's not on the chip looks like. So here would be the qubit chip, and the squiggly line is the readout resonator because it's usually a distributed half-wave or quarter-wave resonator. And that's not enough. So when we drive the readout pulse, its power is really low, like minus 120 dBm. But by the time you detect it over here on the right in this analog to digital converter, for typical electronics, you need like minus 10 dBm. So we're talking about a factor of like 110 dB of gain between the qubit and the detector at room temperature. That is an enormous amount of gain. You get that typically by having a parametric amplifier and then a Hemp-based amplifier at, let's say, 2 or 4 Kelvin, and then a bunch of other amplifiers at room temperature. These amplifiers take up a lot of space and they dissipate a lot of heat. So when you start trying to put a large qubit system into a cryostat, all those amplifiers dissipating heat cause a problem. The cryostat only has a certain cooling power. Moreover, these amplifiers shoot noise out of their inputs, and you don't want that getting back to the qubit. So we tend to have a bunch of circulators or isolators, which are non-reciprocal microwave devices that only allow microwaves to travel to the right and not to the left. Those are pretty big too. Just to give you an idea of scale, this thing pictured here is a low noise factor Hemp amplifier, and you can see compared to the size of the SMA connector how big it is. You know, it's like an inch, inch and a half on the side. So imagine you had one of those for every qubit in a quantum computer with 100,000 qubits, right? I mean, it would like you take up a huge cryostat just to fit all the amplifiers. Now in reality, we multiplex, so we'll have like 6 qubits on one readout line, but even that's not that many. You still are going to have a huge amount of hardware in the cryostat. Not only it takes up a lot of space, they're very expensive. They are typically, sold off the shelf with SMA connectors. So now you have in a real quantum computer, you have like hundreds of thousands of mechanical connectors, all of which has some probability of failing. And if 2 or 3 of them fail, your quantum computer don't work. And like I said, they dissipate a lot of heat. So for those of you in the room right now who might, want to contribute to this field and think readout is cool, I would say that actually making the readout faster right now, it's not really the challenge. The thing we really need to figure out is how to make all this receiver system like small. And there's fascinating research going into that. There are people working on using Josephson junction devices to replace, let's say, the circulators. So instead of having this big magnetic chunky thing that you buy from a company, you would like integrate the circulator onto the chip and it would take up, hundreds of microns of area rather than a giant boxed element. So if you're interested in designing devices, this is a design workshop after all, I would highly encourage you to learn about parametric amplifiers and non-reciprocal Josephson elements because we're all going to need them pretty soon. So it would be like a high impact research direction. Yeah, in my opinion, the scaling issue is more important than faster readouts faster. Just to give you an idea of like how much things have improved, this is a picture of our readout, part of our readout receiver in 2014 when I got to Google. So there's some amplifiers, there's a mixer here, and this is a filter, and it's on this giant aluminum shelf that we put into a rack in the lab. My first project at Google actually was taking all of this and putting it on a PCB just to make it smaller and cost less. So this circuit board, which is about that big, serves the same role as 4 of these shells, which were like each like that big. So when you get into a research environment, a lot of what you wind up doing is in quantum mechanics and all that kind of fancy stuff that you might hear about at conferences and in textbooks and stuff. Like just doing the engineering that you need to make things more reliable and scalable is also really important. Okay, so that's the end. I'll conclude with basically a list of what I think are some useful papers. These 2 here are the foundational papers that introduce dispersive readout. And then if you want to see like kind of what's the latest in the field, that's these recent papers here. Of course, there are many more. I just picked some of the most recent. Thanks a lot.
Time, one in person, one online.
Thank you, maybe talk. I'm wondering if dispersive readout, even though it's really good, is not as scalable maybe as other alternatives. I'm not familiar with the original ones, but do you think there's a chance we could end up exploring some other alternatives for this thing?
Yeah, I think there's a very high chance. It's tough to move away from something that's worked for a long time. But when I look at the hardware overhead of dispersive readout, I wonder often whether some of the old school like flux spacing readouts might be better. It would take, I mean, it's the usual conundrum where in order to actually replace dispersive readout, you have to. So there's a long road there. It can be hard to work on something that doesn't work yet, but everybody else has something that does work. But eventually we might hit a wall. So yeah, we need to.
And then final question, how do we multiplex in quantum for readout compared to classical computing? Because you mentioned multiplexing.
Right. So the way that I'm not sure how to comment on classical computing because the readout for like the DRAM memory is really different. But in the classical case, basically the way this works is you have a bunch of different resonator qubit pairs connected to the same line at different frequencies. And when you send your pulse in, it basically has frequency components at each resonator, and then you demodulate those separately. That's called frequency multiplexing. That's how your radio works. So like when you turn the dial on your radio, you're selecting which frequency to listen to. It's basically the same.
Okay, let's thank the speaker again.